So I want to show you one example of how this plays out in practice. And it's related to our discussion of HQET. So one thing that we said about HQET is that you could calculate the following quantity. So HQET makes some predictions about the B star and the B. They were connected. They were in a symmetry multiplet. And when you took the difference of B star and B, and you took this combination, it actually is purely perturbative, because there's a non-perturbative parameter, but it's actually, if you treat the charm quark as heavy, it's the same for charm and bottom, and it cancels out. So you can actually write down an MS bar operator product expansion, which is technically defined in HQET. And what it looks like is the first thing is just a ratio of Wilson coefficients. So we talked about this, and we plugged in the sort of leading log result, and we saw that it was working actually pretty well. And if you were to kind of look at higher order terms in that OPE, there would be some power corrections to that. They've got some traditional names. The names are not too important. But this is like the analog of the 1 over Q term. Okay, this is the 1 over Q term. This is the leading order term, which is purely perturbative. There's no matrix element here. It's just 1. This is a higher dimension operator. This guy scales like lambda QCD cubed over lambda QCD squared, which is just lambda QCD. So that's like the lambda QCD over Q term. And this is the formula you would write down if you wanted to make a prediction for this thing at higher precision in MS bar. So what happens if I think about this perturbative result at higher orders? So people have actually calculated that coefficient to 3-loop order. And here's what it looks like. So at order alpha, you get minus 0.113. At order alpha squared, you get minus 0.078. And then you get another minus 0.0755 at alpha cubed. Doesn't look so pretty. All right. So each order that you calculate is giving you a correction is about the same size as the previous order. Well, you might say, of course, there's logs. So I should resum the logs. So let's resum the logs. So leading log. And then I get, since I have higher order anomalous dimensions, let me put in next to leading log. And actually, I have one more order, so let me put that in too. 908. Next leading log. Uh-oh. All right, so this is the one that we actually talked about earlier, and that one is actually close to the data. The leading log result was sort of close to what the data was. But when you think about whether that's actually right and you calculate the higher order corrections, you find that you're moving away from the data, right? And again, it's not convergent. Summing the logs has not helped you. And that's because what we're talking about here has nothing to do with logs. It has to do with powers. It's the renormalon that's causing this problem. OK? So we could throw up our hands and say, oh, it doesn't work. Or we could try to do something better. So let me show you what happens if we do some of this stuff that I've been telling you about. So this guy has a U equals 1 renormalon. You can check that very easily by doing a bubble sum. Switch to the MSR scheme. So we reuse our perturbative information in MS bar, but just organize in a more intelligent fashion. So we define a coefficient as above. Saying that this problem must have to do with that renormalon. And then if we write down what the OPE looks like, we have, again, an OPE. And we've changed matrix element definitions as well as Wilson coefficients definitions. So I'm putting everything to scale R0. So that's just rewriting the OPE in this new scheme. When we look at this scheme and we think about what's going on, we want to choose the R0 to be of order lambda QCD, or a bit bigger. And the reason we want to do that is to preserve power counting. So power counting is important when we're making expansions. In some sense, it's key. And if we thought that the original MS bar matrix element was dominated by the scale lambda QCD, we better not screw that up when we make a change of variable. And so the kind of change of variable you're making is you're taking the original matrix element, you're subtracting a series with the proportionality constant R0. This guy was lambda QCD squared, and you want this to be not too far different than lambda QCD, so that this whole thing here is lambda QCD cubed, just like this, so that this thing is still of order lambda QCD cubed. So you don't want to do something like choose the R0 to be, MB or something, because then you'd be making a huge change in the value of this matrix element. You really want to take the R0 cutoff to be of order, say, a GUE or something. So you can use the RG to sum up logs from that scale R0 up to the scale of MQ. So again, we can sum up logs and have a logarithmically improved result. But actually, the most important thing here is getting rid of the renormalon. I just wanted to kind of show you what the result would look like with both the RG improvement, just sort of using the full set of tools that we have. So here's the scales. You have 3 physical scales: B quark mass, charm mass, lambda QCD. You have 2 cutoffs. You have R0, which I just told you should pick to be close to lambda QCD. And then you could think that there's these other scales, MB and M charm, and you'd like to, if this is some low scale and that's some high scale, I'd like to sum logs, and I can do that by running up from R0 to R1, which in this case I'll just pick between MB and M charm. So if you did that, you'd get some result that looks like this. Just putting in some notation for the resummation here. And then this guy is at the low scale. Okay, so now everybody's happy. The Wilson coefficients here can be expanded in perturbation theory. We don't think there's any large logs. This U sums up any large logs between the low scales and the high scales. And this guy's living at a scale that he likes to live at. Okay, and there's no renormalon, no U equals 1 renormalon. So what does it look like if I write down this guy? So first of all, if I look at this thing order by order, this is how the convergence looks. You get a downward shift by about the same amount as before, but the next shifts are small. So the series actually looks like it's converging to something. So that's the first 3 orders if you use this approach. And if you use the complete power of this at the highest order, you can write down that you get this 0.860 from the perturbative part, which is not too far from the 0.88 or the 0.8517, which I said was close to the data. Okay, so this actually is pretty good. You can make some error estimate for how big this thing is. And you can make some error estimate for the perturbative uncertainty from higher orders by varying scales. And you get with a prediction that looks like that. So when you want to estimate uncertainties, what you typically do with your cutoffs is you vary them. You say, well, it has to be up here, but I don't have to take it exactly there. I could take it up here, take it a little lower, move this guy around. That gives you some idea of higher order uncertainties because the dependence on these scales cancels out order by order in perturbation theory. And so varying it is a way of getting an idea of higher order uncertainties from perturbation theory. And that's what I've done, for example, for this perturbative term here. This is varying R1 up and down by a factor of 2 and just see kind of what residual uncertainty you have. This one's more interesting. So that one's like mu variation. This one's more interesting. And that's because we have this other cutoff, R0. But what R0 does is it connects a leading order term to a subleading power term. The R0 dependence cancels between something that's order 1 in the power counting, something that's higher order in the power counting. But when I vary R0, it still cancels between these two pieces because remember I've included in, if you look at the top of the board, I've included higher power terms in my Wilson coefficient. And so varying the R0, you can actually get an idea of how big this thing is, kind of in a naive dimensional analysis type way. And that gives this number here. So R0 variation actually allows you to test for the size of power corrections if you don't know them. And in this case, it turns out that the power correction is kind of small in this scheme. But it didn't have to be that small. It could have been 165, 265. Happens to be 0.065. Okay, so everything looks much nicer after we just get rid of the renormalon. Someone else did the 3-loop calculation. You made the prediction. Which is true in this case. Okay, so questions. So the moral of the story is that if you really want to use calculations that are out there, and you have to think about the physics. You can't just calculate. Sorry. Okay. So these renormalons, when you have kind of order alpha squared or alpha cubed information, then you have to worry about things like this. And if you didn't, what looked like was working beautifully at leading log order might get spoiled. Your leading log might be the best prediction, unless you think about this, that you can make because you're just higher orders, you're getting sensitive to this renormalon problem. And what that means is generically, this is changing, and this is changing. The power correction is changing. And so at each order that this changes, I could compensate by changing this. But it would have to be a pretty big change, right? I change this guy by this amount, and then I have to compensate by that. Oop, now it even changes by a larger amount. Well, compensate by changing this by order 1 amount. That's exactly this fact, that both things have this problem. Order by order, I can cancel out the problem, but I don't want it, but then I can never really assign a number to this. It's an order-dependent number. Each order in perturbation theory that I use here, this number changes. And that's not really what you think of for a physical concept, that this matrix element should have a meaning, that it shouldn't be changing by order 1 depending on the perturbative order that you're working. In this way of thinking, this thing is stable, much more stable anyway, and you can assign a number to it. That's kind of the moral. All right. Yeah. So the thing is that the convergence, it's not about the precision, it's about the convergence, right? So you would be fine in some sense. It would not be technically a problem if this was 0, right? If this guy was that much of a shift, and well, this was a 15 shift, this is a 7 shift. If this guy was like small again, you'd be fine, right? Because then you'd say, okay, well, I extract this thing in the same order that I include that, and and maybe this thing gives a plus 0.07 and this guy gives a minus 0.07, and then I'm close to the data and you're happy. The issue is that you go to a higher order and you get an even bigger shift. That's the real problem, that you don't, in the perturbative part alone, have any sign of convergence. That's the issue. It's not, so the fact that this number is sort of close to that number is, in some sense okay, because you'd think that this thing should generically be of that size. That's what dimensional analysis would say. And dimensional analysis might even say it's a little bigger. So the real issue is that you want your predictions to be stable, and yeah.
I thought that resolution should be higher than the calculation.
So this actually here is connected to that term. I'm saying even if I leave this term out, I actually get something that agrees with the data. And that's because it turns out that the power correction here is this size. And I can get an idea of how big it is by varying the R0 in this prediction. And that changes this number by that amount. And since this thing is also changing in exactly a way that compensates that R0 dependence, I'm getting an estimate for this thing. That's what I did there. So if I were to put this thing in, I'd have a new parameter, and I could exactly fit the data, right? But what I wrote was a little different. Yeah. I kind of went over that quickly. All right. So that's actually it for HQT.